I want to welcome all of you to our another lecture in our video lecture series on design of reinforced concrete structures. In our previous lecture, which was our lecture number 13, we started with the design of beams in shear and torsion. And in that lecture, we looked at some basic formulas relating the value of shear stresses in a beam, and we looked at different types of cracks that can appear in a beam due to the shear stresses. Today's topic will be regarding the behavior of beams without shear reinforcement. So before going into the different types of shear reinforcement that can be used in our beams and the design for shear forces, we will first look at the behavior of beams without shear reinforcement. So today's discussion will be mainly based on the report published by this Joint ASCE-ACI Committee 426. This committee presented its report on the shear strength of reinforced concrete members in 1973, and almost all of our discussion in today's lecture will be based on that report and its findings. So you can just Google this report and also download this report to study on your own if you want to know in detail about the behavior of beams without shear reinforcement. We will only discuss some major portions of this report here today. So on your screen, what you can see right now is we have a simply supported beam at the very top here that has been symmetrically loaded with these two concentrated loads V and V. These two concentrated loads both are at a distance of AV from the support. You can see the corresponding shear force diagram and bending moment diagram for this beam and its loading condition. This is the shear force diagram and this is the bending moment diagram. And on your right hand side, you can see a graph relating to the failure moment, which is given by the product of V and AV and the ratio of AV by D. So when we are studying the behavior of beams without shear reinforcement, we will put all other factors constant and we will only vary this factor here to study the behavior of our beams, that is the ratio of this AV and D. This AV is known as the shear span and this D is the effective depth of your beam. So we will study the behavior of our beams as we vary this AV by D ratio. And you can see this AV by D ratio is plotted on the x-axis of your graph here. As we move to the right, the value of this AV by D increases. That means what we have done here is we kept the value of AV constant, and as we move along to the right, we have increased the value of effective depth so that this ratio as a whole, we have decreased the value of effective depth so that this whole ratio AV by D increases as we move along the right to this graph. So there is one horizontal line in this graph here which represents the full flexural moment capacity of our beams, and this horizontal line you can see at the very top here. We are studying the behavior of our beams for different ratios of AV by D. For example, if the value of this ratio is generally less than 1, we call that as deep beams. Then we study the behavior of short beams whose ratio AV by D is generally, this ratio is generally greater than 1 but less than 2.5. And for slender beams, the AV by D ratio is generally greater than 2.5 but less than 6. And the very slender beams, the ratio AV by D is generally greater than 6. So these are the very short beams, which are also known as deep beams. These are short beams, these are slender beams, and these are the very slender beams. You can see that for these first three types of beams, that is deep beams, short beams, and slender beams, the beam is not able to reach the full flexural moment capacity because the beam fails in shear before it is able to reach the flexural moment capacity, and that is not one of our desired conditions while designing for such type of beams. Whereas if you consider these very slender beams fail in the flexural moment capacity before failing in the shear, so that these flexural very slender beams reach their maximum moment capacity first, and there is no chance for them to fail in shear forces. So if you see this shear compression capacity and inclined cracking capacity here, you can see that there is some region created between these loads at which the beams fail and the flexural moment capacity of our beams. So this shaded region, you can say, represents the decreased or reduced capacity of our beams due to the presence of shearing forces. So we will return to this graph time and again. First, let us study the behavior of these deep beams. For that, we will go to our next slide here. So what happens with deep beams is that deep beams are very short shear span beams, as we discussed previously, for which the 8 by D ratio or AB by D ratio, whatever you may say, is less than 1. Or this value of AB by D is greater than 0 but less than 1, which are also known as deep beams. So for these deep beams, what happens in them is that they develop inclined cracks joining the load and the support. For example, if you see the beam here, these two ends represent the support reactions, and these two are the concentrated loads that we have applied to our beam symmetrically. So you can see some sort of inclined crack develops in these beams that connect the point of this application of load and the support. So these cracks destroy the horizontal shear flow from the longitudinal steel to the compression zone. We have the longitudinal steel here in the beam, which is resisting the tensile forces in the tension zone of our beam. So when these inclined cracks are developed, they restrict the horizontal shear flow from the longitudinal steel to the compression zone, and this behavior changes the beam action to arch action. Arch action means that now this tensile reinforcement of the beam has the same amount of tension force from one end to the other end. So what happens when the behavior of this beam is changed from beam action to arch action? When these inclined cracks disrupt the flow of shear from longitudinal steel. This longitudinal steel that we have here, this serves as the tension tie of a tied arch, and thus it has a uniform tensile force from support to support. And the most common mode of failure in such a beam is an anchorage failure at the ends of the tension tie. At the ends of the tension tie, there will be anchorage failure, and this is also known as shear tension failure. Shear tension failure or anchorage failure. This is the type of failure that is seen in the deep beams due to shear forces. The same is shown in our previous graph here. For these deep beams, there will be shear tension failure or anchorage failure. So what happens for short beams? We saw that for deep beams, there occurs shear tension failure or anchorage failure. In case of beams with short shear spans, that is the value of AB by D between 1 and 2.5. These beams they also develop inclined cracks, as in the case of deep beams. So these beams also develop inclined cracks, but what happens is after the development of those inclined cracks, because of the redistribution of internal forces, they are able to carry additional load. And as that additional load value is increased, the final failure of such beams will be caused by a bond failure or a splitting failure or a dowel failure along the tension reinforcement, or by crossing of the compression zone over the top of the crack. That is also known as shear compression failure. So you can see that shear compression failure in this diagram here. So let's see the diagram here and see the behavior of these beams with short shear span. That means the value of AB by D between 1 and 2.5. You can see some inclined cracks that develop in these beams. And these inclined cracks, after they develop, causes the redistribution of forces in these beams. And as a result of redistribution of forces, they are able to carry more loads. So what happens is that these inclined cracks can also propagate backward in this direction. So when these cracks propagate backward, what they cause is they cause the bond failure. That means the bond between this longitudinal steel and the concrete fails. And when that bond failure occurs, there occurs splitting action, and thus the beam fails by splitting failure. Or what also may happen is that this is the case when the crack propagates backward. When the crack propagates forward, that means this inclined crack is propagating forward and it reaches the point of application of load, and the concrete here in this portion fails by crossing. Hence, the crossing of the compression zone is also one of the failure modes in these types of beam, and this is known as crossing compression failure or shear compression failure. So for deep beams, we saw shear tension failure, whereas for these short beams or beams with the shear span to effective depth ratio between 1 and 2.5, these fail due to shear compression failure. You can also see this shear compression failure in one of the beam tests that is shown here. You can see here various inclined cracks that are developing. Also at the very center, there are vertical cracks developing here. Remember, as we discussed in our previous lecture also, these vertical cracks which start from this tension zone and go vertically upward, these are the flexural cracks, and these cracks are located at the point of your beam where the moment is predominant. That is, if it is a simply supported beam, then at the very center in this zone here where the moment is maximum, these flexural cracks start to appear at this point. But near the support, you can see here these inclined cracks which has also propagated backward, leading to bond failure and splitting failure, and which may also reach at the very top where our load is acting, causing shear compression failure at the very top. So let's go back to our previous diagram. The short beams fail due to shear compression failure, and these shear compression failure are also less than the flexural moment capacity of our beams. But what happens in case of slender beams? Our slender beams fail in diagonal tension failure. This diagonal tension failure we also discussed during our previous class. So what we saw in our short beams was that the inclined cracks extend higher into the beam, as we saw in our diagram a little bit before. So if it was our flexural cracks, they just go up to a certain height. They are vertical, but they do not reach the very top of the concrete. But our shear cracks or our inclined cracks, when they reach to the top of the concrete, failure occurs at less than the flexural moment capacity, as we saw in this graph also here at this point. But what happens in case of slender and very slender beams? In case of slender beams, the ratios of A by D ranges from 2.5 to 6, and for these slender beams, the inclined cracks disrupt equilibrium to such an extent that the beam fails at the inclined cracking load. That is, the beams fail at the inclined cracking capacity or inclined cracking load, and in case of very slender beams, they fail in flexure prior to the formation of inclined cracks. There will be no formation of inclined cracks in these very slender beams. Rather, before the formation of inclined cracks, they have already failed in the flexure. So to sum this up, what we can say is that we touched upon the types of cracks in our previous lecture also. Initially, the concrete is uncracked, but when an inclined crack occurs in a beam at a place where it was previously uncracked, that is known as wave shear crack, as we discussed in our previous lecture. But if that inclined crack starts at the top of an existing flexural crack and propagates into the beam, the crack is referred to as flexural shear crack. So let me see if that diagram is here. Or okay, it's not here. So let me represent what I just said with a diagram. If this is your beam and you see that here we have an uncracked portion. So if a certain inclined crack appears in the previously uncracked portion of your beam, this is known as wave shear crack. We talked about this wave shear crack in our previous lecture also. But if this is your beam which already has some cracks on it, and these cracks further extend into the beam in an inclined way, then these types of cracks are known as flexural shear cracks. So this wave shear crack occurs in beam with thin waves in regions with high shear and low moment. That means near the supports where the shear forces are very high, these wave shear cracks occur. And these are relatively uncommon cracks that may also occur near the inflection point of continuous beams, also near the supports of the simple beams or near the inflection point of your continuous beams. So these are generally not desirable. But these flexural shear cracks, these are the most common type found in reinforced concrete beams. So these flexural cracks extend vertically into the beam, then an inclined crack starts forming from the top of these vertical cracks where shear stresses develop, and these propagate into the beams in this way. So this is about the behavior of beams without shear reinforcement for different values of AB by D ratio. And we discussed all these concepts which are presented in the 1973 paper on the shear strength of RC members, which was jointly reported by the combined ASCE-ACI committee number 426. I hope you have learnt about these concepts well. And finally, before ending today's lecture, let us see what factors contribute to the shear resistance in reinforced concrete members when there are no shear reinforcement. So you can see that there are three different types of force that contribute to the shear resistance. One is this vertical force, which is the shear resistance of uncracked concrete. Another is this tangential force here, which represents the aggregate interlock or interface shear, and another is this dowel fair shear, which is developed in our longitudinal reinforcement. If we had some shear reinforcement here, then this shear resistance would also be provided by this shear reinforcement. But for now, the shear resistance is only provided by these three forces: shear resistance of uncracked concrete, shear resistance due to aggregate interlock, and the shear resistance due to dowel force. So general experiments have shown that this shear resistance due to uncracked concrete is about 20 to 40% of the total shear resistance. Due to this aggregate interlock is about 35 to 50%, and due to this dowel force is about 15 to 25%. And if there were shear reinforcement also, we would add one more factor here, Vs, which is the shear resistance due to our shear forces. So this shear resistance of the uncracked concrete, this is the simplest method of shear transfer by shearing stresses. So this shear resistance occurs only in uncracked concrete or in the uncracked portions of structural members. So the interaction of these shear stresses with the tensile and compressive stresses produces principal stresses which may cause inclined cracking or a crossing failure of the concrete. That means this VCZ may react with the tensile and compressive forces. As you can see here, compressive forces are developed at the compression zone of your beam and the tensile forces is developed in your longitudinal reinforcing bar. This shear resistance may interact with the C and T, and thus inclined cracks may appear in your concrete. So this is the simplest method of shear transfer. Another method is this interface shear transfer or aggregate interlock. This is also known by other different names such as surface roughness shear transfer or shear friction, or also tangential shear transfer. So this is the shear transferred across a definite planar surface where slip may occur. As you can see, this is some form of crack in our diagram here. So if this interface, this is the plane which is under consideration. If this plane is an existing crack, then failure usually involves slippage or relative movement along the crack or plane. This plane as we are discussing now. Otherwise, these tangential forces also contribute to the resistance to shear forces. And finally, the last resistance is due to the dowel forces Vd that is developed in this longitudinal reinforcement. So if reinforcing bars cross a crack, as you can see here, these are the inclined cracks here, and these reinforcing bars are crossing these cracks here. They are meeting these cracks at these points. So if reinforcing bars cross a crack, shearing displacements along the crack will be resisted by the doweling force in the bar, which is in this vertically downward direction. So what happens is that these dowel forces gives rise to tension in the surrounding concrete. And as a result, we can see these splitting cracks along the reinforcement. And as these splitting cracks occur due to these dowel forces, then the stiffness of the concrete around our longitudinal reinforcement will be decreased, and due to that decreased stiffness, the doweling shear also decreases. So these dowel forces which resist the shear forces are not permanent in nature. Because the development of these dowel forces, the stiffness of the concrete around this longitudinal reinforcement continually decreases, thus also decreasing the resistance offered by these dowel forces. So this is about the shear resistance in reinforced concrete members. This brings us to the end of today's lecture. In next lecture, first we will see different types of shear reinforcement, and then we will go through the design steps for shear forces. We'll meet again soon in our next lecture. Till then, stay safe and thank you.